firstly, I just want to say thank you to everyone for signing up, for responding to the poll. Quite honestly, I was expecting around 20 people to respond when we put up this idea. We ended up with over 200 respondents to this workshop poll. So thank you to everyone for responding. Hopefully we can all learn something. I know already with the stuff that we've been developing, I've kind of found a bunch of different bugs and stuff, and it's helped me to push forward what we've done quite considerably. So I'm going to hand over to Paul in a second, but I'm just going to very briefly start by sharing my screen. And yeah, so this is actually the responses from the poll. So just to kind of show you guys a little bit, we asked you a few questions. One of those was whether you used pet thermo tools before. So this is the package that I've built to kind of wrap the alpha melts for Python package to try, and the idea is to try and make it as easy as possible for anyone to kind of go forward, run melts calculations, even if you don't have that much kind of Python or melts experience before. Same with MageMin, actually quite a few, maybe a quarter, just a bit less of people have some experience with MageMin. Tomorrow we will be trying some MageMin calculations. I know there were a few more challenges with the installation. It sounds like a lot of people did manage to find, together we managed to find solutions, and a lot of people have got this installed. If you didn't manage to get MageMin installed, don't worry. It's only going to form a small part of tomorrow's session. The majority of what we're going to be doing is going to be working with alpha melts and pet thermo tools. And then this was the final question we asked, which is kind of a relatively nice split here, of whether you've run Jupyter notebooks before. Over half of you guys either chose no or a little. And so the first kind of session where we're going to run stuff, Penny is actually going to take us through some basic Python functions and kind of like how to work with data frames and things like this to kind of give you guys a bit more of a background over how we're going to be running things within Python as well. And we'll do that with some basic melts calculations in that first session as well. And so just before we start, I want to point out a few different resources. Firstly, we have our Read the Docs page. This is our kind of like documentation for pet thermo tools. If you haven't found it yet, I encourage you to go check it out. This is where we have links to our YouTube videos. We have different kind of example notebooks of example calculations that you can follow through and edit, and various other kind of resources on here as well. Kind of mentioned in that we have the, sorry, I just need to get rid of the meeting controls. We have our YouTube channel. So hopefully, based on a number of views we've been getting, I think some of you have already been using this, but please do use our YouTube examples. They kind of walk through the examples that are available on Read the Docs, and so you kind of give you some more context as to what these examples are meant to be showing. Hopefully they're useful to you guys. We also, if you kind of want to see the actual GitHub repository itself, this is what is kind of linked to Read the Docs. You can also see that. And then finally, the last thing I kind of want to point out is this package has just been put up as a preprint about a month ago now, a bit less than a month ago, in the end of December. And I encourage you guys, if you want to learn more, to read through the preprint, to learn about kind of what we've been planning, how the code structure is set up. If you kind of want to go in a bit more detail about this kind of stuff, I do encourage you to please go and check that out as well. Okay. So I think it sounds like more and more people have been joining whilst I've been chatting. And oh, it was my Discord's coming through, sorry. Let's turn that down. And yeah, so I'm going to hand over to Paul, who is going to take us through a kind of like introduction to thermodynamics and the background behind melts, I believe. So Paul, feel free to take it away.
All right, thank you, Matt, and welcome everybody. This is very exciting. The purpose of this first 45 minutes or so is just to very quickly remind you what thermodynamic modeling is and why we do it in igneous petrology, and then some of the history of how the melts model was constructed by Ghiorso and coworkers. And then I'm going to hand over to Paula to fill you in on the various interfaces that have been developed that we use to actually communicate with the melts model, bringing us up to pet thermo tools, which really for the first time has this unique ability in the same input format and in the same output format to run side-by-side calculations in Melt's world and in Holland and Powell world, which has never been possible before. If you wanted to compare those calculations, you always had to learn two completely different systems, format your calculations for input in two completely different ways, and receive your output in two completely different ways, which made it very awkward to ever compare anything. So that's one of the things that Thermo tools will see is really quite amazing for. So my part, let's see. Does everyone see my screen in a more or less sensible way?
Yep.
Okay.
We can see it.
So we have the Discord open so that without stopping the flow of the whole presentation, if I say anything obscure, or if at any point you have a question, please ask it. Just go to the Discord channel that says day 1, January 12th, 2026, ask for help, and put what you want to ask there. And then there's a separate channel for post your answers. But if you want to thread your responses directly, or if Matt or Penny or Paula want to thread their responses directly to the ask for help, that may end up in that first channel rather than in the second. And as Penny said, it's much easier for us to keep track of questions as they stack up and answer them, and have the questions and the answers there in an organized format if you use the Discord rather than the Zoom chat. Zoom chat is just not very good when there's 100 people online all asking questions at once. So please try to make enough space on your laptop screen to have both Discord and Zoom open so you can follow what we're saying and then also have the discussion go on over there in Discord. That said, I just clicked on the Discord link. Let's not do that. Okay, so what are we doing here? Most of you, I think, realize at this point in your professional careers that petrology is complicated, that most of the processes that we imagine happening in nature, what I would call magmatic paradigms that lead to the formation of igneous rocks, are complicated. They involve processes that are distributed over periods of time, depths in the earth, multiple temperatures, multiple pressures, multiple compositional reservoirs. It's very rare that you can ever do a single petrological experiment that actually completely reproduces the scenario that you want to describe, that might have led to the formation of your rock, or that you might use in the interpretation of your suite of rocks. And so you need some tool that allows you to combine the results of many, many experiments in a way that allows you to test a hypothesis that whatever process you're trying to imagine might actually lead to the formation of the rock that you have picked up. More than that, there is a long tradition in petrology going back decades, almost a century, of reducing the complexity of natural systems to just a few components and developing intuition and knowledge using phase diagrams that fully represent the behavior of those simple systems. And it's a very powerful method, but it never gets you all the way to the end point of understanding what's happening in nature, because there are very few natural systems that really have a small enough number of components that a phase diagram is a complete description, a phase diagram that incorporates all the components at low variance, right? So to deal with distributed processes in space, time, temperature, and pressure, and to deal with systems with 6, 7, 8, 9, 10, 12 components, we need models that handle a lot of the combination of knowledge in many dimensions and in many aspects in order to run a hypothesis test and decide whether we actually know what our rock means. And so to really understand petrology, you need observations, you need experiments, and you need models that combine the results of those experiments in ways that can actually be sensibly compared to observations. And how do you do that? Well, one way to go about it is to construct empirical models, to directly take experimental data that you have, figure out a sensible way to parameterize it and fit functions to it, and then use those fit functions to interpolate or occasionally extrapolate. So I noticed that Keith Paterka is here on the call. Hi, Keith. Keith is a master of this, of developing empirical models that fit data by regression techniques, leading to very useful equations that can very simply be compared to data and that integrate the results of many experiments. And this is fine if you have data that directly address the question you want to ask. But extrapolation beyond those experiments is very dangerous because the functional forms are selected to fit the data rather than to realize underlying thermodynamic principles about the way that phases and components behave in general. There is, of course, a powerful new approach to doing empirical model building, which is machine learning. But again, you have to have data that are directly relevant to the question you're trying to address. If you want to know, for example, the distribution coefficient of iron and magnesium between iron and olivine, you need to measure the distribution coefficient of iron and magnesium between liquid and olivine, rather than many other properties of liquids and olivines that might ultimately lead to a prediction of that quantity, right? So we do thermodynamic modeling because, at least in principle, we can get general models that will apply beyond the calibration set and that will predict properties of the systems that have not actually been directly measured, right? So this is a reasonable approach to doing petrology if you think that equilibrium actually describes what happens in nature to some level of approximation. And of course, igneous petrology is one of the best areas of science to believe that to some extent. And of course, if your thermodynamic model is good enough to actually reproduce the relations that you're trying to predict. So the Meltz family of models has always been one attempt to pursue this idea that if you can construct a general enough, accurate enough thermodynamic model, you can predict equilibrium relations and that these will inform you about natural processes. The Holland and Powell family of models has been a parallel effort for also many decades to do the same thing, leaning a little bit more until recently towards metamorphic petrology, whereas Meltz has always been a tool for igneous petrology, but both of them can operate both below and above the solidus now, and so they can be directly compared. So quickly, I don't want to teach you an entire thermodynamics course in 20 minutes, but the most important equations I think are here. The first law of thermodynamics combined with the second law of thermodynamics leads to the top equation here. Let me get myself a pointer.
Paul, can I interrupt you briefly? Would you be able to mute your Discord? Because every time you get a notification, it's pinging for all of us, and then we can answer questions in Discord without driving everyone crazy with pings.
Absolutely.
Thank you. It's mostly, yeah, just mute the whole channel if possible. Thanks.
I think it is muted.
Matt, you know more Discord.
I think I've just managed to find out how to mute it, mute the notifications for everyone, unless you're.
Yeah, so I think Alex is right. Don't you have to right click on the channel and say mute notifications? If you right click on like the thing on the left hand side, the symbol that's like the alpha mounts all the way on the, yeah. But it's actually the general that's causing it. If you go all the way up, there's like the 3 panels below Caltech.
Mm-hmm.
There you go. But yeah, there you can mute the whole mute server. So 2 up. There you go.
Okay.
Thank you, sorry.
Sure. So the equation at the top here, I was about to find myself a pointer. Can you see my arrow as I point at things?
Yes.
Okay, so this equation says that the total derivative of the internal energy is less than or equal to temperature times the derivative of the entropy minus pressure times the derivative of volume, plus the sum over all the chemical components in the system of their chemical potential times the change in the number of moles. And the simplest interpretation of this equation is that if I manage to hold a system at constant entropy, so that ds is 0, and at constant volume, so that dv is 0, and at constant composition, no exchange of matter with the environment, so that the change in the number of moles of every component is 0, then the entire right-hand side of the equation is 0, and it says dE is less than or equal to 0. And the interpretation of that is that for any reversible process, the internal energy does not change. And for any spontaneous process, the internal energy decreases. And equilibrium is the state where no spontaneous processes will change the state of the system. So the equilibrium is the state of minimum internal energy. Now that's true, but it's not very useful because it's generally difficult to realize an experiment that happens at constant entropy, constant volume, and constant composition. And so we have a series of tricks where we change the independent variables by defining new functions, the enthalpy, the Helmholtz free energy, the Gibbs free energy, and something called the Korzynski potential, which are energy related to the internal energy by adding the product of one or more of the independent variables and the derivative of the function with respect to the independent variables that lead to new statements that describe the predictions of the first and second laws of thermodynamics. And the most familiar is probably this one. The total derivative of the Gibbs energy is less than or equal to minus SdT plus VdP plus the sum over the chemical potentials times the change in the composition. Because this equation says that if I fix the temperature and I fix the pressure and I fix the composition, then any spontaneous process is associated with a decrease of the Gibbs energy, and I can find the equilibrium state of my system by finding whatever configuration gives me the lowest Gibbs energy. That will be the equilibrium. Okay, so most of the time, this is the calculation that we do. We tell a model to hold the temperature and pressure and composition constant, and we minimize the Gibbs energy. But it's important to realize that this is not the only calculation that MELTS can do. You can do an isentropic calculation where instead of temperature, you fix the entropy, and MELTS will do that calculation by minimizing the enthalpy. You can do an isochoric calculation where you fix the volume instead of the pressure. For example, if you're calculating what's going on inside a closed melt inclusion or fluid inclusion, in that case, you minimize the Helmholtz energy. And you can also do a calculation where you exchange the number of moles of O2 in the system as an independent variable with the chemical potential of O2, which is just related to the fugacity of O2. And when you do that, you get a potential function which you can minimize to realize directly the calculation of equilibrium at fixed temperature, fixed pressure, fixed oxygen fugacity, and fixed composition of the non-mobile components. And that's a very useful calculation for doing oxygen buffered equilibria. Okay, so underneath the hood, one or more of these minimizations is what the model is doing every time you ask it to compute an equilibrium. Okay, and the second important thing to realize about all these equations is that you can derive all of these functions, the enthalpy, the Helmholtz energy, the internal energy, the volume, the entropy, if you have a function for the Gibbs energy as a function of pressure, temperature, and composition for every phase that might show up in the system that is differentiable, because the derivatives of G with respect to temperature are entropy, with respect to pressure are volume. Once you know entropy, you can get enthalpy. Once you know volume, you can get Helmholtz energy, and so on. So a model for the Gibbs energy, if it can be manipulated and differentiated, gives you what you need to do all of these calculations and find equilibria. So the central calculation that a thermodynamic model implements is the following. You fix enough variables that the equilibrium is uniquely determined. Usually that's define the bulk composition, and in MELTS the bulk composition is defined by a mass of each oxide component that is in the system. You fix two independent intensive parameters. Normally it's pressure and temperature, but it can also be volume and temperature, or pressure and entropy, or pressure and enthalpy. You can also optionally fix the FO2 and the water activity. I said, or the water activity. Given those constraints, the model then takes the masses of each components and it searches over all the possible ways to distribute those components amongst the phases that it knows about. Phases are things like the silicate melt phase, the vapor phase, minerals, mineral solid solutions. And it finds the distribution of the matter amongst all those phases that minimizes the appropriate thermodynamic potential. Might be Gibbs energy, might be one of the others. And that's the answer you're looking for. Once you know that, you know how much of each phase is present, you know the composition of each phase, you know the density of the whole system, you know a great deal of information. Now, that's just one single calculation. I started by saying that petrology is complicated, and we very often want to do calculations that are distributed over space and time and follow some path that a parcel of material might experience as it ascends underneath a volcano or as it cools in a magma chamber or whatever. And so we can iterate that single equilibrium close to some calculation in a variety of ways by changing the variables in between calculations. So for example, if we slowly lower the temperature in steps and calculate equilibrium at each step, and if we remove before each calculation all the solids that formed in the previous calculation, that's an approximation for the hypothetical process of perfect fractional crystallization. It's stepwise, it's not actually perfectly fractional, it's in little 1-degree batches or whatever, but in the limit of small steps, that converges to an accurate description of a continuous process. So with a thermodynamic model like this that can calculate equilibria, there's a number of ways to use it. You can use it to compute phase diagrams, to show a map as a function of some number of independent variables of what the equilibrium assemblage is. And this is the way many people like to see their thermodynamic models, is in the form of phase diagrams. Sometimes what you want to do is construct an inverse model where you have some data, you have a scenario with a set of free parameters like mantle potential temperature and source composition, and you want to invert for those parameters. And some people want to run forward models. They say, I think I know what happened, I'm going to implement that calculation and then compare what I get to my data. So you can do all of these things with melts, with pet thermo tools, with MageMin, but forward modeling is really the easiest thing to do and the most intuitive and the thing that it was really constructed for. So if you have a scenario that you think led to your observed data, whether it be decompression melting of the mantle or fractional crystallization or an assimilation process, you can simulate that process by repeatedly calculating equilibria while moving along a path, possibly changing the composition between steps of the path in order to describe your process. Okay, so that's what we want to do. We want to calculate equilibria. We want to be able to quickly and conveniently drive equilibrium along some path in pressure, temperature, composition space. In order to do that, you need 3 classes of tools. First, you need models. You have to have the function Gibbs energy as a function of pressure, temperature, and composition with all its derivatives for every phase that might appear in your system. Every mineral, every solid solution, every silicate or carbonatite or what have you, liquid, and the vapor phase. Then you need a set of algorithms that can actually do the calculation, that can take these functions and find their minima. And you need several auxiliary functions that go with the main minimization engine. You have to have a way to choose which phases to put into the calculation, which ones to remove. You have to have an algorithm that recognizes if your phase has wandered into a miscibility gap and wants to split into 2 phases. And you need bookkeeping to do things like add the assimilants or remove the crystallized phases if you're doing something fractional. And finally, you need an interface. You need some way to make setting up the calculation and getting the results back make sense to you, a human, and not just to your computer, and to be able to do the calculations that you want to do quickly and conveniently. Okay, so I'm going to summarize the variance of the melts model, and then I'm going to hand off to Paula to summarize the history of some of the interfaces. And really what you are here today to learn about, or the main new thing that we are rolling out to tell you about, is Pet Thermo Tools, which is an interface to the existing models. Pretty much all of the interfaces that are available share the same algorithms for actually doing the calculation, with very minor differences. Okay, so the models. There are a number of prefixes that get attached to the name melts, and it can be quite confusing to understand what they all mean, because sometimes they refer to different versions of the model, and sometimes they refer to different versions of the interface. So the actual variations of the model, there are only a few, and this is important to realize that the model itself is changed very rarely. It's very stable. And sometimes people write papers using melts models, and reviewers who don't understand this point need to ask exactly what version of the model you're implementing. And there just aren't that many versions, okay? So there was the original melts. It was released in 1995. It is now obsolete. We do not use it. None of the interfaces that are out there support it anymore, for a very good reason that I will explain. There is PMelts, which came out in 2002 and was a recalibration of the liquid model that was optimized for high pressure for 1 to 3 GPa. There is a version called pHmelts that uses a trick to allow you to do calculations that involve very small amounts of water in the system, such as are relevant for describing melting of Earth's mantle, where there's water hiding in the nominally anhydrous minerals, but it can leak out into the liquid. Then in 2012, the rhyolite melts model, its first version, which is 1.0.x, I think currently 1.0.2, came out. And rhyolite melts supersedes the original melts. Okay. In 2015, Ghiorso and Gualda released a model that has a mixed vapor phase and a model for solution of CO2 as well as water into the silicate liquid. And that spawned two new versions, Rhyolite Melts 1.1 and 1.2, which I will explain the difference between them in a moment. Okay. So when I'm done, Paula will come on and tell you about the interfaces that allow you to run these various versions of the model. So which version of Melts should you use? Which model? On Mark Ghiorso's website, OFM, there is a decision tree, which I've just turned into a PowerPoint slide here quickly last night, so it's a little bit ugly. But you follow through these questions. Do you want to model mantle melting with peridotite or peroxenite bulk compositions between 1 and 3 GPa? Yes, use PMelts. No, go on down the chart. Do you want to model crystallization between 0 and 2 GPa using bulk compositions corresponding to natural magmas? If no, Melts is not your tool, right? This is the only thing that Melts does. If you're looking at grossly simplified systems or things that turn up in ceramics that have nothing to do with natural magmas, or you want to do 10 GPa, you're not going to use Melts at all. Assuming you do have a problem that is appropriate to Melts, you go down to the third diamond here. Is a fluid phase present, or does the melt contain dissolved water or CO2? If no, then you can use Rhyolite Melts 1.0. If yes, okay, then are you trying to specifically model quartz-saturated magmas that evolved to the fluid-saturated granite minimum? If yes, Rhyolite Melts 1.1. If no, which is every other system that has CO2, basaltic systems, alkaline systems, then Rhyolite Melts 1.2 is the model of choice. Now let me explain why the chart works this way. So we had the original Melts model. It came out in 1995. It made a bunch of predictions. It very quickly became apparent that at high pressure, it made some systematic errors. And you can see here the series of experiments by Baker and Stolper on melting of fertile lertzolite at 1 GPa. This is silica versus melt fraction. and the prediction from melts in the green line of what the silica in those liquids should be. And when melts and these data came out, nobody actually realized that silica went up at low melt fraction during melting of lertzolite. And so the fact that melts predicted that was kind of remarkable, but nevertheless, it's off by like 3 weight percent in the silica content. That's not so great. So pmelts was created by adding lots more high pressure experiments and making some other modifications to the equations of state underlying the model, which leads to the red prediction, which is much better. Also, here you see the experimental temperatures and the temperature at which the model yields the same melt fraction as the experiment. And, oh, I've got in pink, you see what melt says, and you can see it's systematically off at 1 GPa by 100 degrees, right? Whereas pmelts is off by less. So pmelts is better for modeling peridotite melting at mantle pressures, but there are still errors. It's not exactly right, all right? The other thing, and this is important to realize, is that at low pressure, at ambient pressure and pressures less than a few, maybe half a GPa, pmelts is not better than melts because of the assumptions that go into the formulation of the model, that the mixing parameters are independent of pressure, and because our knowledge of the equations of state is imperfect. When you add more high pressure constraints, the model gets better at high pressure, but it gets worse at low pressure. And so the introduction of pmelts caused the spawning of 2 parallel models, melts and pmelts, one for high pressure, one for low pressure. It would have been nice if pmelts were just better everywhere, but it's not. So now we have these 2 versions of the model. Then in 2012, Gil Gualda and Mark Ghiorso got around to addressing the fact that there were very few quartz-saturated experiments in the melts calibration database, and the behavior of the model at high silica is very sensitive because the activity composition relationship is very flat in that region. And what they noticed is if you take melts and you simulate crystallization of the Bishop Tuff, that you have this distributed crystallization interval that's like 100 degrees wide. And if you look at it in projected quartz albite orthoclase space, the Bishop Tuff composition is here. When you crystallize it in melts, you have feldspar on the liquidus, and so the liquid evolves toward quartz before it finally reaches a eutectic and crystallizes. And the actual Bishop Tuff doesn't do that. The actual Bishop Tuff is very, very close to the wet granite minimum eutectic, and it should crystallize over a very narrow temperature interval. They were able to fix this by adjusting the standard state properties of quartz and sanidine within the experimental uncertainties to produce a model that says the Bishop Tuff is eutectic and goes from all liquid to essentially all solid over the very narrow temperature interval. And that's remarkable, and it stimulated a great deal of interest in melts modeling from people that work on felsic systems, granitoid systems. In alpha melts, there are a few further adjustments to the rhyolite melts model that we have implemented. Like we realized that they adjusted quartz, but they forgot to adjust cristobalite and tridymite, and so the silica phase diagram was wrong, but we've tweaked that up. So the important thing is that if your model does not involve quartz saturation, then melts and rhyolite melts are identical. So it doesn't matter which one you use. And if it does involve quartz saturation, then melts is wrong and rhyolite melts is right. So there's no reason ever to use the original melts model. That's the reason that it is obsolete. As of 2015, Ghiorso and Gualda did this extensive calibration of the properties of CO2 and water in the vapor phase and in the silicate melt, yielding very accurate predictions of the solubility of CO2 and water in mixed vapor systems. Okay? In order to get this best fit to the behavior of water and CO2, it was necessary to adjust the parameters that describe the way water dissolves in the silicate melt. And unfortunately, when that happened, the model no longer has this magic property that rhyolite melts 1.0 has of very accurately fitting the wet granite minimum. And the result of that is that the model spawned new versions again. Rhyolite Melts 1.1 includes CO2, but it keeps the older water mixing parameters. So it works well on rhyolites that are CO2 bearing. But to have the best degassing predictions in CO2 bearing systems where you don't have to worry about quartz saturation in the granite minimum, you want to use Rhyolite Melts 1.2. So that's the reason that there are the 4 different versions of the model that are supported and are in common use. Okay, all of the models have a library of minerals that they can potentially crystallize from the melt. Some of them are just pure solids. They're one component. All you need to know is their standard state properties. Okay. There is the fluid phase, which is just a mixture of water and CO2, or in some cases, just pure water. There are no reduced volatiles in it. There is the possibility of crystallizing iron-nickel alloy as a solid or liquid if you're very reducing. And then there's all of these solid solutions, and this is where a great deal of the richness comes in. I want to emphasize, so we have the pyroxene solid solutions, we have the olivine solid solutions, we have garnets, we have feldspars. In some interfaces, feldspar is a single phase that can be alkali feldspar or plagioclase. In alpha melts, they've been separated so that we can give them different partition coefficients when we're doing trace element modeling. There's a simple binary biotype model. There is a complex solid solution of spinels in the general sense, which extends from spinel proper, MgAl2O4, through hercinite, chrome spinels, magnetites, and ulvospinels. So all of those are called spinel, but you have to look at the composition of your spinel to see whether it's a chrome spinel, an aluminum spinel, a magnetite, an ulvospinel. It can be any of those things. There is a solid solution called rhombohedral oxide, which includes ilmenite, Fe2 plus TiO3, and has some solid solution towards hematite, towards pyrophenite, towards deculite. So if you're looking at 2-oxide oxybarometry, you're going to be looking at equilibrium between the rhombohedral oxide phase and the spinel phase, which is kind of a strange way to describe an ilmenite-magnetite equilibrium, but that's what it is. There are a couple of very simplified amphibole models in there also. There are a bunch of things that we know are missing from the mineral models. There are some important components of pyroxene that are not included in the pyroxene model. There are some important components of garnet that are not included in the standard garnet model. There are lots of important components of micas that are not included. There are lots and lots of components of amphiboles that matter. And this is important, right? Even if you write a perfectly accurate model of this simple hornblende phase, it's very unlikely to crystallize in any actual calculation. And that's because real amphiboles have lots of minor components. They have vacancies in potassium on the A site. They have manganese and titanium. They have fluorine. They're slightly non-stoichiometric. And all of those things raise the entropy a lot and therefore lower the Gibbs energy a lot. And that's what makes amphiboles so stable in so many igneous systems. So until you write down a fully complex amphibole model that includes all those minor components, it's very hard to get it to behave the way you want it to behave. And so amphibole is one of the major shortcomings that we are working on, but nobody has really produced a satisfactory result yet. Okay, in the solid solution models, you construct an accurate thermodynamic solid solution model by deciding how many sites there are in your crystal structure and which ions can go on which site, and then describing the compositional range of variation that is available and choosing order parameters that describe, if you have the same ion that can go on multiple sites, how it gets distributed between the sites. And usually you don't have to worry about this if you're just running the model, but there are a couple times when you do. In particular, In the pyroxenes, this is the way the pyroxenes are expressed. They have some components that you've heard of, like diopside and Hedenbergite and enstatite and jadeite to get sodium in there. But the ferric iron, aluminum, and titanium contents of pyroxene are expressed using these three components that were made up for this purpose. And you can see that asenite has ferric iron and aluminum, bufonite has titanium and ferric iron, and aluminobufonite has titanium and aluminum. So each of them has two of those elements, and by linear combinations of these three, you can get whatever amount of those three elements you want. And some of these components will be negative, and that is fine, as long as it corresponds to a zero or positive amount, a non-negative amount of the actual ions on the sites. But one result of that is if you try to use melts in a simplified system that, let's say, has aluminum, but it has no ferric iron and no titanium, for example, right? No titanium means that the amount of bufonite must exactly cancel the amount of aluminobufonite, so the titanium adds to zero. And computers make round-off errors. They can add a positive number and a negative number that they think are the same, and they add to -2 times 10 to the minus 16. And then, in order to implement the model and calculate the entropy, you have to take the log of that number. Taking the log of a negative number causes the model to crash. So, in general, whenever you're using melts, which is intended for natural systems, you want to have a non-zero amount of aluminum, ferric iron, and titanium. It can be very small. It can be 0.00001 grams, but you shouldn't try it with zero. Okay, the real heart of melts is two things. One, it's all those solid solution models that were constructed by Sack and Ghiorso starting in the late 80s. And it's the model that treats the thermodynamics of mixing in the silicate liquid, which is descended from Mark Ghiorso's thesis work at Berkeley with Ian Carmichael. The fact is we don't have a general framework for a completely accurate thermodynamic model of silicate liquids. Their structures are too complicated and too time dependent to be described in a way that leads to a tractable model. You have to have some kind of heuristic way to capture what's going on in the liquid. So the choice that Meltz makes is to describe the liquid as if it were a mixture of these simple mineral-like molecules. Okay, so all the magnesium is treated as if it were moving around in either forsterite molecules or picrochromite molecules. All of the iron 2+ is moving around as if it were in phthalate molecules, and so on. And once you've made that assumption, which is not true, it is an approximate description, okay, you can then write down a formula that gives you the Gibbs energy of that liquid with certain parameters that you can tune. And this turns out to be, 35 years of experience has shown, good enough to make a lot of meaningful predictions in igneous petrology, even though it isn't exactly true. Okay, so the excess parameters that describe the mixing between those molecules are tuned by fitting to large sets of experimental data where you have solids coexisting with liquids that you believe are at equilibrium. We assume we know the chemical potentials in the solids, and then the chemical potential function in the liquid is adjusted to, as accurately as possible, reproduce the equilibrium relations from those experiments. For every version of the model up through rhyolite melts 1.1, the number of components in the system and the number of species that are used to describe mixing in the liquid are the same. But when CO2 was added, Ghiorso and Gualda realized that you needed both a CO2 molecule and a carbonate group in order to capture the behavior of CO2 all the way from rhyolites to basalts. So there is a degree of freedom in the model where it can speciate the carbon between these two forms. Okay, when you come along and ask Meltz to do an equilibrium calculation, it follows this flowchart underneath the hood. And way back in the 1990s, you could actually see these steps going past at a rate that your eye could register. Now it's all much too fast for you to follow, so just know that this is happening underneath. You have to have some initial guess of the equilibrium state, okay? And the interface will help you set up that initial guess. There is what we call the superliquidus initial guess and the subsolidus initial guess. Superliquidus is you're trying to find an equilibrium at some pressure, temperature, and bulk composition. Assume as your initial guess that the system is above the liquidus and consists of entirely liquid, where the liquid composition equals the bulk composition. Because the liquid is so free to move around in composition space, that's almost always a valid initial guess that you can use. But sometimes it's a real nuisance because you might be doing calculations that are subsolidus or very close to the solidus. And so in order to avoid having to go through this loop 5 times just to get to your starting point, in alpha melts, you can also use a subsolidus initial guess, where you distribute your components amongst solids in a way that adds up to the bulk composition. Once you have your initial guess, you can ask whether any other phases should be added to the system. If the answer is yes, you add the phase. If the answer is no, you go ahead and minimize your thermodynamic potential, like Gibbs energy or one of the others, distributing the matter that you have between the phases that are currently in the assemblage. Then you can ask, are any of the phases trying to disappear? Their mass is going to 0. If so, you can take them out, loop back, and equilibrate with a smaller group of phases. If no, you can ask whether any of the phases want to split into multiple copies of themselves, like 2 pyroxenes or 2 feldspars or 2 liquids. If so, you can add an extra copy. You can go back and now equilibrate again with your longer list of phases that includes both copies. If no, you can ask whether there are any more phases that should be added. If yes, you loop back, you add them, and you go again. If no, you're done. You found equilibrium, and you can report that state back out to the interface to be saved in the output file, to be graphed, to be updated for the next step of the calculation, where usually once you have an output from the previous calculation, you know what your initial guess is going to be, and you can just keep looping. Okay, it is 8:50. I think that's my time limit. So I'm going to stop here and just show this last slide that I call the good, the bad, and the ugly about melts calculations or thermodynamic models in general. The good is they are often quite accurate. They give you satisfying results, and you can use those results to test a very wide range of hypotheses. And because the model is constructed in a general way rather than simply parameterized to fit some particular data set, it can surprise you. It can do things you did not know that it can do. I was very surprised to discover that rhyolite melts 1.2 predicts the existence of carbonatites, even though it was not trained to do that. Okay. You can track many useful properties. You can simulate very complex processes. And with modern interfaces, you can build scripts that run very complex, large-scale jobs efficiently and quickly without a lot of typing at the keyboard. The bad is actually sometimes the models are inaccurate, and you don't always know when that is going to be true. It requires testing and some intuition and some history with the model. The handling of minor components is often unsatisfying. There are phases that are just not complicated enough to predict what actually happens with those phases in nature, like amphiboles. And for some purposes where you need to run millions or billions of calculations, the model remains too slow for practical use. The ugly is sometimes it just crashes on you or refuses to converge. And in many cases, there are workarounds for these crashes and convergence failures. And the lesson we want to give you in this workshop is you don't give up if the model fails on you once. You use some of the tricks we're going to teach you to work around those crashes and failures and get it to behave, because very often it will. Okay.